So in the second part of the biosafety, laboratory biosafety lecture, so we will be discussing now about biological safety cabinets. So biological safety cabinets, or BSCs as they are called, are designed to protect the operator, the laboratory environment, and work materials from exposure to infectious aerosols and splashes that may be generated when manipulating materials containing infectious agents. So for example, when do those happen? Of course, shaking the flask, basically when transferring loop transfer, basically when you are working working in your laboratory, even in pipetting. So these infectious agents can come from primary cultures, from the stock solutions, and some diagnostic specimens as well. So these infectious aerosols are these are the one of the most actually main concern. That is why we use BSCs. So small invisible aerosols may be inhaled or may cross-contaminate work surface materials. So basically, you need to prevent those aerosols from getting out of the laboratory, or even the containment area, which is your BSC. So when properly used, BSCs have been shown to be highly effective in reducing laboratory-acquired infections and cross-contamination of cultures due to aerosol exposures, because aerosols happen, and they are usually invisible to us. And remember, the agents that you are handling in a biological laboratory are, of course, microscopic. So the BSCs also help protect the environment by, of course, containing the infectious agent inside and preventing their escape. So one main component of the BSCs is the HEPA filter, or the high efficiency particulate air filter. So the addition of the HEPA filter is a major improvement in the design of the biosafety cabinets. So the HEPA filter traps 99.97% of particles in a 0.3 micrometer diameter and a 99.99% particles of greater and smaller sizes. So this the HEPA filters is basically how does it filter off it entraps the smaller fragments, basically basically they intercept. It is actually you have here fibers. The filter sheet is made up of randomly arranged fibers. So they have pore sizes. They have varying pore sizes, but there is thickness to them, so that even if some particulates manage to pass through some of the pores, because it's they have many random threads intersecting inside the filter, tendency is that you have more or less an interception. Even if the particle is small enough to pass through, it can still be intercepted because of the thickness of the filter, and of course the randomly arranged fibers. So the HEPA filter effectively entrap all known infectious agents and ensure that only microbe-free exhaust air is discharged from the cabinet. So the second design modification was to direct HEPA filtered air over the work surface. So this is an additional design to some BSCs, whereas you want to protect not only the environment but also your product. This is usually applied if the laboratory is designed to handle sensitive cultures such as stem cell cultures and other tissue cultures. You do not want microbials or viruses infecting your culture. You want to protect your culture, so you apply HEPA filters to the influx air as well. So they provide protection of work surface materials from contamination. They are also called product protection because the biological material you are working on is a product, because of course it's a stem cell or even a pharmaceutical product, and you want to protect it from outside contamination. So this is a brief overview. So we have 3 classes of biosafety cabinets. So class 1, class 2, and class 3. Actually, class 3 is known as the Glovebox, as you can see later. Now, we also have a laminar hood. And what's the difference between a laminar hood and a biosafety cabinet? As you can see here, the airflow in a laminar hood. A laminar hood also has a HEPA filter, and a fan, and it's actually, if you look at it, it's very similar to a BSC, but there is a major difference. Laminar hoods are also known as the horizontal and vertical outflow cabinets, or the clean air workstations. They are not BSCs because, as you can see, the flow of the air here, they filter the incoming air and direct the clean air to the product, because this is the work area. You are going to use the work area here, and the air from the work area can go outside without any filter. So here, the laminar hood, rather than protecting the environment, the purpose of the laminar hood is to protect your product and not the environment, because as you can see, the air from the work area just simply goes out to the environment. So laminar hood must not be used in handling pathogenic substances, because you are just directing the pathogens outside. So the flow of air is again towards the personnel. So if the thing you're handling here is infectious, your personnel will be infected, because again, the direction of the air is towards the personnel. Now let's look at the by BSC by type of protection required. So for these groups 1 to 3, of course, you can do a class 1, a class 2, or a class 3. So for personal protection, microorganisms in risk 4 group, class 3 must be used. So personal protection in risk group 4, again, you can use also class 1 and class 2, but within the laboratory. For a product protection, class 2 or class 3 only if you consider a laminar flow. Then volatile nuclide or chemical protection in minute amounts, the class 2B1 and class 2A1 with an outside vent. And a volatile radionuclide or chemical protection, class 1, class 2B2, and class 3 biosafety cabinets. So what are those classes of biosafety cabinets? So here is the class 1 biosafety cabinet. So in a class 1 cabinet, it's designed mainly for personal protection. So as you can see here, it allows the entry of the room air. So the outside air can enter. That means there is basically no product protection. That is why in our selection here, if you want to protect the product, the one you are working on, you do not use a class 2 cabinet. A class 1 cabinet, because it allows, the main feature of the class 1, it allows ambient air to go in. It only filters the exiting air, because once the air enters the work area, it becomes considered contaminated. So it must be filtered when it goes out. So you have here the front opening. The front opening is also where you put your hands through, so you can work on the work area. So this is the work area. You put your hands through the opening, and this is your sash. The sash basically is a glass. Of course, it's glass. You need to see what you are working on. So you have a glass view window here. That's the sash. So in some cabinets, it can be opened or closed. Basically, you can raise it or lower it to, of course, to accommodate the things that you put inside. And then you have an exhaust HEPA filter and an exhaust plenum to direct the air. So it's not recommended for working with sensitive biological samples, of course, due to the inflow of air. So air coming in through the front opening and exiting through the HEPA filter. For the class 2. So the class 2 is designed not only to provide personal protection, but also to protect work surface materials from contaminated room air. So we have basically 4 types: A1, A2, B1, and B2. So they can be used for working with infectious agents in risk groups 2 and risk group 3. So they can be used for working in infectious agents in risk group 4 when positive pressure suits are used. So this is BSC class 2 A1. So as you see, we have A1, A2, B1, B2. So we will only be discussing some basics class A1 here and B1. So here is your front opening. So your hand goes through here. So the difference between BSC 1 and 2 is having your air curtain, basically. So BSC 1, your air, the ambient air, doesn't necessarily goes into the work area here, but rather it passes through a an opening, an airflow, an air inlet here that passes through uh, your blower that that can be filtered. So basically, an ambient air, it doesn't enter your the work area. How do you prevent it from entering? Of course, there's also an airflow coming from the top going down. So there's an airflow here, so that prevents the ambient air from the outside entering. And then there's a blower. You have two HEPA filters. The HEPA filter that directs air outside, the exhaust here, of course, it's also filtered, and another filtered air that goes to the inside of the area, and which is basically your workbench. So your work, basically your workstation or your work area, is receives a cleaned or filtered air. So basically, you have product protection here, and then the contaminated air after is also filtered. So basically, this is your class 2A1 BSc. And then we have class 2B1 Biosafety cabinet. So in a class 2B1, so similar to a class 2A1, you have a sash. You have your front opening, and the sash can be lowered or exited. So you have here the airflow. You have HEPA filter here. So one difference, a HEPA filter here. So the air, again, the ambient air doesn't enter the work area because of an air curtain from the top. And then the air flows to the two blowers, which is again circulated in the BSc. So some of them goes out, again filtering it, and some of them goes here. You actually have another set of exhaust HEPA filter. So you have this BSc class 2. So this connection of the cabinet exhaust to the building exhaust system is required. So some of the differences in the BSc class 2 and class 1, 2, and 3 biosafety cabinets. So in a class 1, you have here your basically there is no recirculated air because most of the air is the ambient air, and all of them is exhausted. So in a class 2 A1, 70% of the air is recirculated, 30% is through the exhaust. So one of the main differences between A1 A2 is the velocity, actually mostly on the manufacturing makeup of the biosafety cabinets. And then you have your B1, 30% of the air is recirculated and 70% of the air is through the exhaust. And then you have a class 2 B2, no recirculated air, all of them are through an exhaust. And a class 3. Class 3A, there is no recirculated air, any air is through exhaust. So the class 3, which is known as the Glovebox, this is your class 3. So here, instead of a front opening, you basically have that. The reason why it's called the Glovebox, you have here these are openings for the gloves, a glove ports. So you have an arm gloves. So basically, unlike the biosafety class 2s and class 1, where you can just shoot your hand and arm through the opening and then work around, here you need to place your hand inside the gloves. So your arm doesn't enter the work area, but you just manipulate things through your glove box. So you have here, of course, the sash, the viewing sash, and a double exhaust HEPA filter here. So double HEPA filter here. So to, of course, to be sure in preventing the escape of the harmful substance inside. You have a double-ended autoclave pass-through, or also known as a pass-through box. So because here, unlike the class 2 and class 1, where you can lower or put up, so you can you have an ascending or descending sash. The sash here is basically fixed. You cannot actually move it. So the only way to put your pathogen or your culture inside is through this pass-through box, or it's a double-ended autoclave. So it also sanitizes things going in or going out. And then you have your chemical dunk tank. So if you have here water, basically water, parang wash off, run off water. So you have a dunk tank for that. So you have here a HEPA filtered air. So in terms of circulation of air, this is through the ambient air is filtered going in and double filtered going out. So the air circulation is just through these ports. So this is your BSc Class 2 Glovebox. Now, aside from the biosafety cabinet, some of the personal protective equipment used in the laboratories, you have, of course, the laboratory gowns, lab coats, and also coveralls. So they help they correct the hazards of contaminating the clothing. So it prevents your clothing from being contaminated. So the best laboratory coat is actually a back opening coat, because for our research, for our class laboratory in school laboratories, we are using the front opening lab coat, but the best lab coat is actually the back opening, because of course, you consider why is it better for a back opening, because when looking at PPA, the front area, your front area is always the dirty area, and your back is always the clean. So you need to know which is clean, which is not clean. So the front is dirty, the back is clean. So having an opening at the back is actually a measure to keep the inside safer, or the inside clothing cleaner. And then you have plastic apron. So again, for clothing contamination, the feature of this one is waterproof clothing. Footwear against impact and splash. So it must have a closed toe. Sometimes some laboratory might require you to have a shoe rag. Aside from your shoes, you must also wear a shoe rag. And then goggles for impacts and splashes to protect your eyes. Actually, one of my problems with goggles is because I'm wearing spectacles. So it's difficult to wear glasses on top of my spectacles. And then you can also have face shields or side shields. So safety spectacles, similar to goggles. So you have impact resistant lenses. So for people, if you have the money, you can buy safety spectacles that are all that can be optically corrected, or your prescription glasses, the lenses, your safety glasses that also has your prescribed lens grade, if you have the money to do that. Anyway, face shields. Shields the entire face. It's easily removable in cases of accident. Actually, face shield has been well known to us right now, because with this pandemic, we are using face shields as well as masks whenever we go out. And then respirators is usually seen in the levels 3 and level 4, BSL 3 and BSL 4. So it prevents inhalation of aerosol. So aside from the mask, respirators designs include a single-use disposable, full face or half face air purifying, full face or hooded powered air purifying or supplied air respirators. And then you have gloves. It prevents direct contact. Never ever conduct a microbial laboratory without gloves, even if it's a biosafety level 1. You must always wear surgical gloves. So disposable microbiologically approved latex, vinyl, or nitrate gloves. These are for hand protections, and having a mesh gloves if you're handling sharps. So for disinfection and sterilization, so let's first define some terms. What is antimicrobial? Antimicrobial is an agent that kills microorganisms or suppresses the growth and multiplication. So when we talk about antimicrobial, it doesn't 100% kill. It sometimes just suppresses their reproduction. Antiseptic. Antiseptic is a substance that inhibits the growth and development of microorganisms without necessarily killing them. So antiseptics are usually applied to body surfaces. Biocide is a general term for any agent that kills microorganism. And a chemical germicide is a chemical or a mixture of chemicals used to kill microorganisms. So, when we have the contamination, any process for removing and or killing microorganism. So we can also use, the same term is also used for removing or neutralizing hazardous chemicals and radioactive materials. Actually, when we talk about decontamination, we always think about chemical spills rather than actually microbial infection. When we talk about in biological decontamination, this is usually antimicrobial or disinfecting. So, disinfectant is a chemical mixture or mixture of chemicals used to kill microorganisms, but it cannot kill spores. So, that's one problem with disinfectant. And unlike antiseptic, it is usually applied to inanimate surfaces or objects. So, when we talk about antiseptic, usually apply it to body surfaces such as alcohol. When you talk about disinfectant, it is applying it on tabletops and other non-biological surfaces. So actually, this is important because you do not use disinfectant, or it is not advisable to use disinfectant on your bare skin. So disinfection is a physical or chemical means of killing microorganisms, but not necessarily spore. That's one thing. One thing about disinfections, it cannot kill spores, unlike say your antimicrobial or even sporicides. So microbicides is a chemical mixture of chemicals that kills microorganisms. So by microbicide and biocide, basically they are quite synonym of each other. Biocide, chemical germicide, or antimicrobial. Now sporicide is a chemical mixture used to kill microorganisms and spores. So here you include spores, because of course spores are very difficult to eradicate. Sterilization is a process that kills or removes all classes of microorganisms and spores. So in terms of a wide range, so sterilization is a higher spectrum than simply disinfection. So let's look at some chemical germicides available for the laboratory. So the most common one is chlorine or sodium hypochlorite. So it is a fast-acting oxidant and is a widely available and broad-spectrum chemical germicide. It's normally sold as bleach, which is an aqueous solution of sodium hypochlorite, which can be diluted with water to provide various concentrations of available chlorine. The downside here is it's highly alkaline and can be corrosive, even to metals. So activity is considerably reduced by organic matter. So even if you use chlorine on, say, slimes, it's difficult to actually use them, especially if the microorganism has established its own biofilm. Biofilm means a lot of organic matter, proteins and glycoproteins. It actually protects the microorganisms inside. So sometimes bleach is not enough. And then we also have chloramine. Chloramines release chlorine at a lower rate than hypochlorites. Because it releases a slower rate. If you want a more proactive type of chloramine, you need to have higher concentrations for efficient equivalent dosage. But the good thing about this one is, since it's a low rate, it releases chlorine at a lower rate. It is not necessarily inactivated by organic matter to the same extent as hypochlorite solutions, and virtually odor-free. So, since it releases chlorine at a lower rate, items soaked in hypochloramine must be thoroughly rinsed to remove any residue and bulking agents in it. And of course, the soaking time is longer. And then you have chlorine dioxide, which is a strong and fast-acting germicide, disinfectant agent, and oxidizer. It's often reported to be active at concentration levels lower than those needed by chlorine as bleach. But since it's gaseous, it has its own health risk. And then we have formaldehyde. Formaldehyde is a gas that kills all microorganisms and spores at temperatures above 20 degrees. However, it's not active against prions. Prions are proteins, proteinaceous infectious agents. So, it cannot do anything against proteins, in short. Glutaraldehyde is active against vegetative bacteria, spores, fungi, and lipid and non-lipid containing viruses. So it's non-corrosive and faster acting than formaldehyde. So, but for bacterial spores, it usually takes several hours, but still effective. Then we have phenolic compounds. Example of that is triclosan. So they are active against vegetative bacteria and lipid viruses when properly formulated. But because it's phenolic, there are some health concerns in their use. By the way, triclosan is an active ingredient in your soap. And then alcohols. Alcohol such as ethanol and isopropanol is active against vegetative bacteria, fungi, and lipid-containing viruses, but not against spores. Now, the highest efficiency known for ethanol and isopropanol, or ethyl alcohol and isopropyl alcohol, is the 70% solution. So, a solution greater than or lower than 70% is not as effective. So, you have a lower efficiency if it's greater than 70, and even if it's lower than 70. So, that doesn't mean that if you have a higher, say, 90% alcohol solution, it's more effective than 70. It's not. 70% is the ideal maximum efficiency. So, iodines and iodophores is similar to chlorine. Its effectivity is actually similar to chlorine, but the problem here is iodine stain materials. Have you seen betadine? So, it's made up of iodine. Aside from that, it's toxic. And then, hydrogen peroxides. They are strong oxidant and broad-spectrum germicide. They are quite desirable because they do not produce toxic waste material. Hydrogen peroxides, although as an oxidant, when they degrade, you just have water. Okay, so this is the end for the laboratory biosafety. So the references for this lecture is from the WHO Laboratory Biosafety Manual, 3rd edition, and from the CDC Biosafety in Microbiological and Biomedical Laboratories, published in 2009. So thank you for listening.